It's a great pleasure to introduce the first speaker of this morning, Professor Wolfgang Ziller from University of Pennsylvania. And the title of his talk is Manifolds with Positive Sectional Curvature.
Thank you very much. It's a great pleasure to give a talk in a conference in honor of Marcos for his 60th birthday. So happy birthday, Marcos. Belated birthday, I think. Oh, maybe the first question that's on everyone's mind. Luis, what's plan B? Okay, so I will talk about positive curvature, and I will give shortly some kind of overview of some of the main results and maybe some conjectures. But before I do that, let me write down right away the main theorem that I want to get to eventually, which is a new example of positive curvature that I constructed recently in joint work with Carsten Grover and Luigi Vadiani. So the theorem states the following. There exists a 7-dimensional manifold which has positive curvature. So my notation for sectional curvature will be sec. So it's a manifold which is mid-symmetric with positive curvature, which has the following properties. So I'm going to list some properties just to make it kind of appealing. The first property is that it has a very large isommetry group. So the isommetry group, or at least the identical component of the isommetry group of this metric, is SO4. And if I look at the quotient of the 7-manifold by this 6-dimensional isommetry group, I get an interval. So the quotient is 1-dimensional. So it's as close to transitive or homogeneous as one can get. So one property is it has a large isommetry group. And another property, which also tends to be out important in constructing the metric, is that there exists a fibration, but only in the orbifold sense. So exists the orbifold fibration, in fact, the principal fibration. SU2, the group that is the structure group with fibration, or the prince, is the SU2, and the quotient is S4. But it only is a fibration in the orbifold sense, and the set of orbifold points, at least in R4 here, is very easy to describe. I look at a very nice embedding of RP2 into S4, and the metric on S4, the induced metric on S4, is everywhere smooth, except that if I look at this RP2, then normal to the RP2, the metric is not smooth. It has an angle 2 pi over 3 instead of 2 pi at all points in the normal space of the RP2. Okay, and this projection here is a Riemann submersion. In fact, the fibers are also totally geodesic, so the kind of vibrations that Harold was looking at yesterday also. Another property, which is an a posteriori property, which we did not use this in our construction, is that one can say something topologically about the manifold, namely P7 is homeomorphic to the unit tangential bundle of S4. And this follows from surgery theory, so one knows that abstractly it must be homeomorphic to the unit tangential bundle of S4, just from its homology, in fact. We do not know whether it's diffeomorphic to the unit tangential bundle, but say from general surgery theory, for example, it follows certainly that is at least is a unit tangential bundle connected with some exotic 7 sphere. So that just follows from general theory, but we don't know whether it's diffeomorphic. Okay, so this is a new example I want to get to towards the end, but let me first put this into context by talking about positive curvature in general. So what does one know about positive curvature? I should also say that both these properties, A and B, are crucial in the construction of the metric. So we use both properties, the fibration property and also that the isommetry group is very large. This group SO4 here acts on P. It actually takes fibers to fibers and induces also an action on S4. So maybe I should say that at least. So induce an action on S4 turns out to be an action by SO3. Again, S4 divided by S3 is an interval. So this vibration is respected by this kind of very large group action. And both the vibration property and the group property is used very strongly in constructing the metric. Okay, positive curvature. Let me maybe first say a few things. What does one know in low dimensions? So certainly when n is 2, one has one of the first global theorems in my geometry, the Gauss-Bonnet theorem, says that that M must be S2 or RP2. When n is 3, in the 80s, Hamilton proved the theorem that under the weaker assumption of positive curvature, M must be a quotient of S3 divided by the finite orthogonal group. When n is 4, there's no classification. There is a conjecture, or various conjectures, of what should happen in this dimension. So let me formulate it, say, usually goes in the name of Hopf conjecture. We should say that if I have a 4-dimensional manifold with a positive curvature, then it should be S4 or RP4 or CP2. Okay, that's the one version of the conjecture. Usually it's formulated in the form that there should be no matrix of positive curvature, so none on S2 cos S2. That's the usual formulation of the Hopf conjecture, but that's probably the version that one should try to understand or prove. And of course, one can also generalize this kind of product question more generally. Are there any metrics of positive curvature on a product manifold? Or maybe another, say, conjecture might be that if you have a symmetric space of rank greater equal to 2, can they admit metrics of positive curvature? So these are various versions of the Hopf conjecture. And I should mention some progress in this direction was made, in fact, quite recently. So this is a theorem that in its first version is due to Shang and Kleiner, then can be improved by topological results of Fintuschel. And the final version was proved recently by Grover and Wilking. So it says that the Hopf conjecture is in fact true if I make an additional assumption. So N4 positive curvature, and I add to the assumption that S1 acts by isometries. So I have at least some non-discrete isometry group. Okay. And then the statement is that M is in fact equivariantly diffeomorphic to one of these models. So Shang and Kleiner in the 80s proved that this assumption implies it's homomorphic to one of these standard models. And it was later observed that if one uses some topological results by Fintuschel on general circle actions, one can actually improve this to a diffeomorphism. And very recently, Grover and Wilking showed that in addition, one can also recover the group action. The action must be a usual action, an isometric action in these models. Okay. So under a circle symmetry, one can say exactly what happens. This theorem motivated lots of work afterwards to study manifolds with positive curvature, with many isometries, which are a large isometry group. And this property A in our theorem is, goes in that direction, was important. Okay, so this is dimension 4, what one knows in dimension 4, what is conjectured dimension 4. In dimension 5, one can also formulate the natural conjecture would be that M5 positive curvature implies that the manifold is a quotient of S5 divided by a finite group of isometries. That's probably the version in dimension 5 that one should expect. And here there's a theorem by Rong, which says that this is true if a T2 acts by symmetries. Although I think he has to assume simply connected. So simply connected 5-manifold with positive curvature, where T2 acts by symmetries must be diffeomorphic to S5. So in high dimensions, one has to enlarge the symmetry that one requires in order to get some conclusion. In dimension 6, things are already completely unclear what should happen. Of course, one has the 6-sphere and CP3. But now one also has non-standard examples, so which aren't spheres or projective spaces. And there's one due to Wallach, which is a flag manifold, U3 divided by a 3 torus. So that has a metric of positive curvature. And there's one more, which is somewhat similar, which is due to Eschenburg, where I take U3 and I divide on the left by a circle and on the right by a 2 torus. So my 3 torus now parameters by 3 unit complex numbers, R, S, and Z. And I divide on the right and on the left, and I get a new 6-manifold. And Eschenburg shows this also has positive curvature. This is sometimes called a flag manifold, and that's called the inhomogeneous flag manifold. And these are the known examples in dimension 6. It's a very interesting open question, say whether possibly could there be infinitely many examples in dimension 6 with positive curvature. So that's certainly wide open. Okay, so this much about low dimensions. Let me now mention some abstractions. So what's known about abstractions in general in high dimensions? Topological abstractions. And again, the most classical theorems in global remaining geometry belong in that category. Of course, there's Boni-Myers, which says that Ricci curvature positive implies pi1 finite. And in positive section curvature, one can do better in even dimensions. So that's Sinch. Even dimensional manifold with positive curvature as pi1 trivial or Z2. These are known topological abstraction to positive curvature. They have to do with a fundamental group. And a very important and basic question in the subject is the following, that if I start with a metric with non-negative curvature, so I have a manifold, I have a metric with non-negative curvature, they're easier to find. Then the question is, I can formulate in various ways, how do I go to positive curvature? Either are there abstractions, say topological abstractions, to go from non-negative to positive curvature, or also more concretely, if I have such a metric, how can I deform the positive curvature, or what are the abstractions to deform the positive curvature? So that's a very basic question, and there's very little known about that. And these abstractions on the fundamental group are, in fact, the only known abstractions to go from here to here. Okay, that's kind of surprising. So for example, if I take an RP2 cross RP2, it has non-negative curvature but doesn't have positive curvature. But if the manifold is simply connected, there are no known abstractions, which is kind of surprising. One certainly expects the class of manifolds with positive curvature to be much smaller than non-negative curvature. But so far, nothing is known of that type. So let me maybe because there are topological abstractions to this class of metrics, which of course implies abstractions here also. I'll just take one of them, which is a due to Gromov, which says that if I have a manifold M with a non-negative curvature, this implies that all the Betti numbers of the manifold, say with an arbitrary field of coefficients, is bounded a priori only in terms of dimensions. So if you take a sufficiently many connected sums, you cannot emit a non-negative curvature anymore. There is a famous conjecture for this class of manifolds, which also has implications for positive curvature. So let me discuss this a little bit. It's a beautiful conjecture. It's called the Bott conjecture, which says that if I have a manifold with non-negative curvature, this should imply the following condition. I look at the loop space of the manifold. I look at the sequence of Betti numbers of the loop space, again with some field of coefficients. And the sequence of numbers should go at most polynomially in I. So this is at most polynomial in I. In general, the sequence of numbers goes exponentially. So this is a very strong topological condition that these Betti numbers go polynomially. If I put here the rational coefficients, these manifolds are called rationally elliptic. So here it's usually called elliptic, so i.e. M is elliptic. And this ellipticity condition has strong implications. Topologies have a lot of results in this direction. Let me just mention that in dimension 4, so I'm now describing consequences of this condition right here. In dimension 4, the only manifolds that satisfy this property are simply connected. These manifolds. And it so happens that these are also known to admit non-negative curvature. So this gives you a classification non-negative curvature if you want to. In dimension 5, one knows that the only manifolds that have this property are S5, S2 cross S3. There's a twisted bundle, which I can describe as S3 cross S3 divided by the Hopf circle diagonally. And then there's a symmetric space. These are the only manifolds that have this property. Here it's even with rational coefficients. This is also true. Here I also need torsion coefficients. This result is due to Paternine. Is this right? Forget the other co-author. Whereas this is not so hard. So other consequences of this condition. So again, I describe consequence of this condition here in high dimensions. It implies that the Euler characteristic of the manifold is greater or equal to 0. Again, that's another Hopf conjecture, that a manifold with non-negative curvature has non-negative Euler characteristic. Again, nothing known about that conjecture. And there's a second Hopf conjecture in this direction, that if I look at an even-dimensional manifold with positive curvature, it should have positive Euler characteristic. That's another version of the Hopf conjecture. And under this assumption here of ellipticity, one knows that this is positive if and only if the odd Betti numbers are 0. So if you want to, then this version of Hopf conjecture should maybe say not only should that be positive, all these should be 0. Maybe that's what one should prove instead. So this ellipticity assumption has all kinds of restrictions on the topology. Okay. So much about known obstructions or conjectures. Now let's talk about examples. And so I want to discuss a little bit, say, 4 properties or constructions that are useful or interesting in positive curvature if one wants to look for new examples. First one is a classical one that has been studied a lot, where I take quotients. So one typically here starts with, say, a compact Lego. Say, start with the metric of positive curvature in the base, positive curvature in the fiber, and somehow choose a horizontal distribution, make it remain submersion, and then it's much more difficult to control the curvature in the total space. It's the wrong way around in the remain submersion formulas. Right? So that's a much more difficult proposition. But nevertheless, since all examples have this property, this should be understood better, what perturbations in positive curvature. And the last property or question one should study is this kind of deformation question I mentioned earlier. How to go from non-negative curvature to positive curvature. In fact, all the known examples over here, one can also view in this fashion that one starts with a certain metric with non-negative curvature and then deforms it to positive curvature, although that's something one kind of observes after the fact. There is some recent result by Peter Peterson and Fred Wilhelm, where they, for the first time, I think, looked at this deformation question more seriously in a non-trivial example, and they showed that there exists an exotic seventh sphere with positive curvature. So the seventh sphere was, in geometry, is described as a Grohr-Meyer sphere. It's a certain biquotient, it's non-negative curvature, and they showed that one can deform, although it's not a short-time deformation. In fact, it's a composition of seven different kind of deformations they have to do, control the curvature in each case, and the arguments are quite delicate. This is a very long-time difficult deformation. But this is a recent example which uses this kind of structure. Okay. So let me get back now to the new example I mentioned in the very beginning. So how did we find this manifold? We certainly weren't looking at manifolds homomorphic to the unitary bundle S4. Clearly, this was not our intent. We tried to understand this question of largest homotopy group. I mentioned earlier that if the homotopy group is so large that it acts transitively, then they have been classified. So one knows all the homogeneous space of positive curvature. And therefore, the next natural question is, assume that the homotopy group is not transitive, but as transitive as it can be. And here we proved the classification theorem. So this is joint work with Carsten Grover, Volker Wilking, and myself. So we assume that Mn is compact, simply connected, positive curvature, of course, and say Gx bisometries. Some G group Gx bisometries, such that it's large but not homogeneous, such that the dimension of the quotient is equal to 1. So the quotient must then be an interval, since M is simply connected. These are some called homogeneity 1 manifold. So these are the assumptions, and what's the conclusion then? Of course, one has, say, all the compact rank 1 symmetric spaces, fields and projective spaces. They have many such actions on them. They're all classified. One has, let me just write down other known examples. So among the known examples, there are a few of them that admit a group action which has a one-dimensional quotient. I won't write them down. They're all known. And of course, we were hoping to get something new out of this classification. And indeed, there were a sequence of manifolds that we could not exclude in this kind of classification attempt, namely, or one of a sequence of manifolds. In fact, two sequences of manifolds in dimension 7, and then there's a lonely guy, which only occurs once there. Where in each case, the group that acts is, well, let's say, at least locally, is SU2 cos SU2, or SO4, SO3 cos SO3. So that's the group here which has this property. Group is 6-dimensional, so the quotient can barely be 1-dimensional. It is. And on these manifolds, we do not know whether they have positive curvature. Okay. So call these candidates for positive curvature. And that's, of course, the next question been studying for a while. So let me first say some properties of these manifolds. The first one is just a 7-sphere. First one in the Q sequence is a Wolof space. It's also a known example of positive curvature. They all admit non-negative curvature. Old result by Carsten Grover and myself, or corollary of such a result. Topologically, they're all different. So, for example, for the pk family, pi 1 and pi 2 is 0, and pi 3 is zk. They're of different homotopy type. Similar for the Q family, they are not too connected. Pi 2 is z, but then H3 is Z2k plus 1, I think. Anyway, they all have different homotopy type, and somehow the P and Q family are different, at least topologically, although geometrically in a certain way they are similar. So the theorem I wrote down in the very beginning is now that P2 admits a G-invariant metric with positive curvature. So I think G in this case is SO4. So the first one in the sequence where nothing is known is the example where we're able to put a metric of positive curvature on this, and then the isomorphism group under this large isomorphism group. Before I go on, I should also mention that there's some independent work by Derricott. So he has another metric on the same manifold P2 with positive curvature. It's of a different type. The metrics are a different type. I may be able to say something more later on how they differ. But at least as far as the work I've seen so far, the proof in the end that the metric it describes a positive curvature is still a numerical proof using maple pictures. But it's the same manifold. So this was also done recently on, so these are kind of 3 papers that appeared recently over the last year or so in positive curvature, as far as new examples are concerned. Okay. So this is my large isomorphism group structure. Where does the fibration structure come from? Well, inside SU4, I have an SU2, let's say left multiplication by quaternions, for example, sits inside SO4. SO4 acts on a manifold, so I can simply divide by it. In fact, we can do this for the whole family. Right? So here's my family PK. I look at, I divide by SU2. Turns out that SU2 acts almost freely. Doesn't act freely, so the quotient is not smooth. Has finite isotopy groups. That means that the quotient must be an orbifold. And it turns out that this orbifold here is homomorphic to S4. So for the whole sequence of manifolds, I get this kind of orbifold principal bundle structure. And for QK in a similar fashion, I can also divide by SU2 or SO3 in that case. Not so important. And that's CP2. Again, with a certain kind of orbifold structure. So both of them, because of the large isomorphism group, also come associated with that with a certain bundle structure, an orbifold bundle structure. Okay. And that's another property that I want to use. So let's go back a little bit and see, well, how does one use this kind of bundle structure to construct metrics? So given a file bundle or principal bundle, what is the natural class of metrics one can look on them? Well, the geometrists have some very natural kind of metrics that they call connection metrics, or physicists call them Kaluza-Klein metrics. So let me describe a little bit what they are. So I look at a principal bundle. Doesn't matter if it's an orifold sense or a manifold sense, everything carries over exactly the same fashion. As long as you do local computation, it doesn't matter. You have, say, given a metric on the base, and given a metric on the Lie group, Lie group G, for example, a binary metric. Let's say it's a binary metric. So now I have something on the base, I have something on the fiber. I need a horizontal space, and for a principal bundle, that's given by a principal connection. So that later be a principal connection. So then one can put these together into a metric on the total space. By saying that on the one hand, I just project onto the base take inner product on the base, and then I add to that, take theta of x, theta of y. Right, theta of a vector ends up in the Lie algebra of the group. So now I have two elements in the Lie algebra, and I take the inner product, the binary metric on the fiber. So this defines a metric on the total space. The projection pi then becomes a Riemann submersion. G sub G. Back in geometry, one often adds in a twist that one scales the metric here and gets a one-parameter family of metric. See in a minute why that's a good idea. So in this fashion, pi becomes a Riemann submersion. The fibers are totally geodesic. And the fiber on the metric on the fiber is, of course, my given binary metric. Induced metric on the base, of course, is my given metric B. The horizontal space, as you can see here, is a kernel of theta. So all the principal connection does is describe horizontal space to you, and then I put the metrics together into Riemann submersion. The fact that these fibers are totally geodesic means that curvature properties are much easier to describe. So that's one reason why these metrics have been studied a lot. And it's often very useful to let t go towards 0. So shrink the fiber down to a very small size. So in our case here, where we have these kind of fiber bundles, the fiber is S3 with a binary metric, so it's a round sphere. These are all totally geodesic inside pk. I shrink the fiber, and the curvature in the fiber blows up to infinity, and should give me a much better chance to get positive curvature on the total space of the bundle. So very natural to let t go towards 0 in this kind of situation. Okay. So maybe there are various, one can study the condition on the principal connection for these kind of metrics to have positive curvature. What's the condition on theta and the metric on the base and the curvature of the principal connections to have positive curvature? One can study that in detail, but maybe I won't have time to go into that too much. So this has to do with what is called fatness. There's a concept of Weinstein, where I looked at fat bundles. So we actually observed that simply the property that all two planes on the total space, which are spanned by a vector tangent to the fiber and by a vector orthogonal to the fiber, so horizontal two planes, the property that they have positive curvature or is a very strong property on the bundle. It's called the fatness of a fiber bundle, which Weinstein introduced a long time ago. And in fact, more recently, I also looked at topological extractions of fatness with Louis Fourier in terms of characteristic classes, Chern classes, or Pontryagin classes. So there are many restrictions that one gets from the positivity of a curvature of these kind of special two planes. And if one requires all curvatures to be positive, then it becomes a strong property on the curvature of the principal connection. And that's, so I call that hyperfatness in some of my own survey papers. And this was a condition that was discovered by Dajczer and Rigas, but maybe I won't get into that now. Okay. So I haven't described our manifolds yet, right? I've only said that there's a sequence of candidates, dimension 7. I said that the large group X bar assemblies, but I haven't told you yet what the manifolds are. Right? So at least let me try to describe the manifolds in some concrete fashion. In fact, there are two ways to describe it, by using either one of those properties. I could describe it in terms of group actions, which is a little bit more involved. I don't want to do that. Or I can describe it by trying to describe the vibration. So I'm going to try to describe the vibration that I just erased. So, which will then give you a concrete description of the manifold. So I start with the base. Remember, our base was S4 for the other manifold CP2. So I start with S4. And I don't put a manifold structure on S4. I put an orbifold structure on S4. And remember, the way this is supposed to go is that I have a Veronese RP2 inside S4. And the metric is smooth except for orthogonal to the RP2 direction. So there must be an angle, say 2 pi over k. So for each integer k, I get a certain kind of orbifold structure on the 4 sphere. Okay. And I'm going to now fix k and look at the geometry of this kind of orbifold. Well, if I can then say put a metric on it, an orbifold metric on it. I can put an orientation on it, and then I also have a star operator. So I choose an orbifold metric. Plus an orientation. Then I have the star operator, which goes from lambda to the tangent space to lambda to the tangent space. Because in dimension 4, that introduces all kinds of important properties. Particularly, I have what I call the self-dual forms. So those two forms which are fixed by the star operator. Okay. So there's a splitting of the two forms into self-dual two forms and anti-self-dual two forms. I can look at this bundle of self-dual two forms. That's a bundle now over my orbifold. It's an orbifold vector bundle. Right? So this fiber here is 3-dimensional, since T is 4-dimensional. So I have a 3-dimensional orbifold vector bundle over S4. And now I can look at the frame bundle of this vector bundle. So that HK is the frame bundle of this 3-dimensional vector bundle. So this now becomes itself an orbifold principal bundle over the 4 sphere. So the structure group of this that acts on the frame bundle just by rotating the frame doesn't act freely anymore. And the reason is that the space here is not a manifold, it's an orbifold here. So the frame, changing the frame has isotropy. So this is a kind of natural description of a family of manifolds. And it turns out these candidates over there in this language are described as twofold covers of these manifolds. These aren't simply connected. So if I look at H2k plus 1, I get pk. If I look at the twofold cover of H2k, I get qk. Particular k is equal to 2, so for P2, that corresponds to H3. H3 corresponds to normal angle 2 pi over 3. But this game I can play for any normal angle to this Veronese RP2. So in this language, they have a very uniform description, these manifolds. But when I take the twofold cover, the topology is very different for these. Okay, so now describe the manifold. So that's my manifold in terms of the vibration language, probably the simplest way to describe them. And now I want to put an orbifold, a connection metric of this type on this bundle. But in addition, as I said, we have we have a large isometric group, which in this picture here I can describe as follows. So I claim that this orbifold structure on S4 has a large symmetry group. Namely, there's an SO3 acting on S4. Some of you know this in terms of, say, isometric submanifolds. This is an example you do Cartan. The orbits are hypersurfaces. Of course, then they have constant principal curvatures. So that's what Cartan was interested in. Geometrically, one describes this in terms of conjugation on symmetric traceless 3x3 matrices. And then one also knows that if I look at the orbits of this action, that's exactly one way to view very neat surfaces. They're on orbits of a very natural SO3 action on S4. So this acts on the base of these gyrations. So here I have an SO3 acting. Of course, this is now a principal bundle, so I also have this SO3, the frame, change in the frame acting naturally. So on this total space here, I get a large isometric group acting, SO3 plus SO3. Okay. And if I go to the twofold cover, this will become SO4 or SU2 plus SU2, so up to covers. That's how I get this large group action on the candidates I described earlier. So I want to use verbation property, and I want to use also this large action property. So let me just say roughly, going into detail, how can I put these two together? Well, I have to describe the metric only. So remember, the quotient is one-dimensional. So for example, the base here, S4 divided by SO3, is simply an interval. So I should imagine this to describe a metric on S4. But I have to first find a metric on S4. I have the orbits by the SO3 action. These are hypersurfaces. I can look at a geodesic orthogonal to the hypersurfaces. And it's pretty sufficient to describe the metric along this geodesic orthogonal to the hypersurfaces. And at each point on the geodesic, it just becomes a homogeneous metric on this orbit in the manifold. So therefore, one can describe that by functions along the manifold. So a metric on S4 is invariant under SO3 is described by three functions. V1, V2, and V2, three functions of a time t along the normal geodesic. It's kind of like, if you want, like a warped product metric. Of a somewhat non-trivial nature, namely, say, t is the direction of the geodesic, and then normal to that, I have three functions. With theta 1, theta 2, and theta 3, I say the usual basis that I get of the Lie algebra of SO3, and therefore also of the forms on the manifold. So it's kind of a warped metric on the base. And of course, the other ingredient was, that's a metric on the base, the other ingredient was a principal connection. But again, this principal connection I only have to describe along a normal geodesic, so theta can be described by three more functions. So that's the geometry of the metric, the description of the metric by three functions on the base, describing the metric on the base, and three functions describing this kind of principal connection. And then eventually I will let theta go to 0 also to improve the situation. In our examples, so I'm not going to write down the functions. I'm just going to say that these B and H are piecewise polynomial. So I divide my interval into three pieces, and on each piece it's just a polynomial of order at most 5. So they're fairly simple functions. And now the difficulty becomes, well, I have my metric described. How do I prove there's positive curvature? And that is, turns out to be a very difficult difficult question. Say, particularly when the dimension is, the larger the dimension gets, the more difficult it is. Even as a linear algebra problem, that's probably the main reason. The algebra problem is hard. See, I give you a vector space, and on the vector space I give you a curvature tensor. And how do I prove that this curvature tensor has positive section curvature? Just at that point, this linear algebra problem. That's a very difficult linear algebra problem. And I'm sure that, say, for example, if I compute the curvature, so in our examples, one can compute all the curvatures, all components of the curvature tensor in terms of these functions, the first and second derivatives. That's not so hard. One can write this down. But if I now have this tensor in a basis, are there, for example, finally demanding conditions on the components of the curvature tensor that would be equivalent to positive curvature? So is it a final condition? I'm sure the answer is no. So that means it becomes very difficult to somehow decide. Of course, the section curvature is a function on the Riemannian. So one has to show the function is positive on the Riemannian. That's a very difficult problem if you want to prove this. Even numerically, that's not so easy to do because the Riemannian is very large, although it's compact. Trying to do something like find the critical points of this function are hopeless. It's way too complicated. Even in simple situations, one can't do that. Like the simple situation, we have tried this once and I couldn't do it, is just take a half fibration where the fiber is S3 and shrink the fiber. So you get a one parameter for a metric, a Berger type metric. Compute the critical points of the section curvature of this metric on the Riemannian. It's hopelessly complicated. Okay. Although in that case one knows when you have positive curvature. So let me explain an important ingredient that we use in order to kind of get around that problem, that it's so difficult to show that a tensor has positive curvature. And that's a beautiful trick that's due to Thorpe. Like now we can forget everything I said and just maybe come away with one beautiful idea at the end of the talk. That's something that's kind of obvious when you see it, but clearly very powerful and beautiful. This is due to Thorpe. So I take a vector space, I take a curvature tensor on a vector space. So I want to discuss this linear algebra setup. Right? I have a curvature tensor on a vector space. And as usual, I can regard this as a symmetric endomorphism from lambda 2t to lambda 2t. Okay. And of course, the section curvature is then described by, let me write it down. Just to make the trick transparent. This, of course, is a Euler curvature tensor applied to x, y, z, w. Up to sign. So this is description of our hat as a symmetric endomorphism. From this formula, of course, it's obvious that if I know that our hat as a symmetric endomorphism is positive, so if this is positive whenever x wedge y and z wedge w agree, that certainly implies positive curvature. Because that's what my section curvature is, right? So if it's positive definite as an operator, then certainly it has positive curvature. And of course, this will be a simple linear algebra property to check, right? I have a symmetric endomorphism. I want to see whether that symmetric endomorphism is positive definite. That's a simple linear algebra question. But this property is much too strong. Namely, there's a recent theorem by Boehm and Wilking, which says that under this assumption here, one actually has that M must be a quotient of a sphere. So only quotients of spheres have this property that the curvature operator is positive. So that's hopeless. So therefore, one now modifies this. By doing the following. Namely, of course, this curvature tensor has certain symmetry properties and the Bianchi identity, and now I'm going to destroy the Bianchi identity by choosing a 4 form on this vector space. This also, again, naturally induces a semantic endomorphism by the same kind of formula. So alpha hat applied to x wedge y in a product with z wedge w is alpha x y z w. Again, it has, now I can regard it as a Curvature tensor with the usual symmetry properties, except for it doesn't set for Young identity. But now simply add that. So look at the modification. Add this kind of symmetric endomorphism to R hat. Okay. Again, you get a symmetric endomorphism. And now observe that if I look at the section curvature of R hat alpha is the same as for R hat. Right, if I'm supposed to take, so section curvature of xy would be R hat alpha x wedge y, x wedge y. Well, I'll put that into the formula here. Of course, in the first term, I got just the usual section curvature. And in the second term, I take xy, xy, and I get 0. So this here goes away once I take a section curvature. So now, of course, then Thorpe said, well, if I can find alpha such that this modified operator is positive, this then implies the section curvature is positive. Okay. And this, again, of course, now is just a simple linear algebra kind of question. Is this a positive definite matrix or not? And that's a very powerful method. Thorpe discussed this a long time ago. I forget how long, actually. He was only interested in dimension 4 for this question. And what he showed was that in dimension 4, it's actually does everything you want in the following sense. That if I have a metric in dimension 4, and I want to compute the maximum of a section curvature, then there exists a 4 form such that if I look at this modified operator, its largest eigenvalue is a maximum section curvature. If I want to find the min, then there's a possible different 4 form, such that the smallest eigenvalue of this operator is a minimal section curvature. Because none of these are curvature operators of any metric. It's just an algebraic trick. And for max and min, you have to choose different 4 forms. There's no reason why it should be the same 4 form. It gives you both max and min. That was Thorpe's observation. And in higher dimensions, this is not true anymore in the sense that there are examples of curvature tensors on a vector space, say, where which have positive section curvature, but such that there's no 4 form such that modification is positive. So it's not guaranteed to work anymore in high dimensions. But nevertheless, it's certainly a powerful tool how to reduce this question to a kind of linear algebra type question that one can attack. In our case, the metric was described by polynomials. One has to choose very cleverly choose a 4 form. Of course, this is one of the difficulties in this trick here is how do I find the right 4 form? And that's certainly one difficulty we had to overcome, find a clever 4 form, which again is described by polynomials. I look at this operator, it becomes a matrix, a large matrix. The entries are now rational functions, the quotients of polynomials. I want to check it's positive definite, so I can just use Sylvester's theorem described by determinants. And in the end, each condition becomes here simply that a certain polynomial must be positive. So our proof in the end boils down to show that a collection of polynomials has no real zeros, is positive. And there one can use something called Sturm's theorem, which counts real zeros of polynomials in order to prove that the polynomials that arise in our construction indeed are all positive. So this Thorpe trick was essentially in our proof. Maybe I'll stop now. Thank you.
Are there any questions or comments?
Could you say something about why the fiber bundle doesn't have singularities over the orbifold singularities of the base?
Yes, of course you have to convince yourself of that. That's not quite obvious. You have to examine this along the Veronese RP2. And the simplest way to understand that is by looking at the full frame bundle. So here's a simple fact that if I have an orbifold, then if I look at the frame bundle of the orbifold, it's smooth. The frame bundle of an orbifold is a smooth manifold. And the examples that we get here are quotients of the full frame bundle, which is an SO4 principal bundle by a subgroup, by SV2. And now I want to understand the isotopy of the full frame bundle on this kind of special orbifold singularity and see that they don't lie in the group I divide by. And that one does explicitly. So one studies the frame bundle, and then, which is smooth, but of course that's now 10-dimensional. And my 7-dimension is a quotient of that, and I can understand the isotopic groups. So that takes an argument. It's not obvious.
Any more questions? Well, if not, let's thank Wolfgang again.